Yeah, let's see, because zooming in will confine our board space to so much. Plus we move the camera around intermediate. All this motivates me to get back the old camera.
Yeah. Have you seen there's the camera mounts? They're attached to you. Camera's out, so when you walk around, it's
The whole camera.
Cool. All right, looks good.
You are connected over there in Zoom, yeah?
Yeah, it's on his Zoom.
Then no need to connect for me.
So it's good.
Yeah, if that we can read, then no need to connect for that.
Is it readable?
Oh, there's nothing written on the
If-
board.
Oh. Make it small for this way.
Oh, yeah,
That one we can read very easily.
very well.
Yeah.
So a little smaller review.
Yeah.
Yeah.
That okay, let's try smaller. This one is
That is still, they're both
No.
still readable, but I'd say the middle line is about as small as you want to go.
Yeah, I don't think that's I do like this.
okay. Let's go a little bit bigger than second one. Close to first, but bigger than second. Oh, from here we can read.
Okay, that's
We'll not do from here. That's why we'll do from here. Second one we can read. If we go a little bit bigger, then we are good.
okay. Then we don't have to do anything.
Yeah, we are good then.
Okay.
I already mentioned you that the video quality of the mobile is better. We get 720 pixel, but with this laptop or Zoom video, we get 360 pixel.
Yeah, I understand that. The challenge is that when it is on the mobile, it is not allowing me to upload it. The upload speed probably for the internet is not that good, even using the department. So I keep trying for 12 hours and a few days, and it doesn't do. So because it's 5 GB, like because it's a 720, what do you call it, pixel?
Yeah, I think we
This
can
is a
transfer
5
to
GB.
the computer that one. That should be faster.
But
if you
I connect to Linux, so this doesn't connect to.
okay, if you have like the airdrop.
Yeah,
then
so
you
if
connect
you
very
allow me,
fast.
I can pass it on to anyone. Once Jackson did it, it seems too complicated, that's all, on a daily basis.
If that becomes more complicated.
Let's see this, how it is.
Okay.
Like today, apparently it is good. I think what we have to be more careful of. So the video that we were looking for is probably on that day, the manual focusing was not done for.
Exactly.
Does that make sense? So I removed the autofocus from here. And then I had to make sure that I focus it correctly. Otherwise, the whole lecture is bad. Let's see if this is bad, then we look for all those options. In fact, what I might consider is that I'll get the old camera, which has this setting. We have a remote for that. I don't think the new students have seen that. But that seems much more to.
And that one was very clear at that time. Last semester we used.
Last semester, exactly. So we'll try though, we'll go back to that. Yeah, we'll see. But thanks for the feedback. Keep asking me this, only then it will get fixed. So we had the midterm, I graded it, I put it back in your mailboxes. And was that satisfactory? Was the midterm satisfactory?
Next question.
Oh, yes, sure. On the questions itself, okay, right, yeah.
For number 5, what is the question? You said A is greater than 1.
Uh-huh,
What was that? 1 over A?
yes.
But if A is like 15, then only put only outside the unit circle.
Yeah, I didn't understand the question, but apparently you guys fixed it on your.
If I was just dividing by two, whatever I came up with
Divide by 2.
in my head,
Oh.
not for the exam. That was
Oh, instead of 1 over A, you were dividing A over 2.
like when I was analyzing, I didn't.
As
Yeah, it affect my case.
Yeah, it is 1 over A, right? That's called inversion in general, if you're familiar with this transformation. Whenever, or imagine a world where you invert about a sphere of radius 1, how it will look like. So it's a popular transformation, it has a rich physics in it, and it has, let's put it this way, photon not having mass is associated with a transformation like that. But it has a lot of physics in there, yeah. Okay, any other questions on this? So here are the averages. All the lights on. That one. Does it change?
Yeah.
Oh. Here are the midterm scores. There was a full score. And. Right. Now I don't remember whether this is midterm or the total. Probably midterm, right? Otherwise a full score, because the homework will take away at least sometimes. There is one comment I wanted to make. Usually there is a correlation between homework and midterm. That correlation was not there in this, which means that at least some of you are not being responsible with the homework. Like you should use resources. I encourage you to use resources, but at the same time, you should fix it by studying on your own also. So that was one comment I noticed. That one thing that I noticed is that correlation is not there. But that's averages. And Sanya is a full scope. Keep up those.
But we are 8, but there are 7.
Yeah, right. That's 7. I don't know. Don't ask me hard questions. 4 plus 3 is 7. Yeah.
It's mine, let's just do it. I think more.
Yeah.
Yeah. Actually, what I do is that I go to D12 and then record this. So
Not on the link.
Ian is not there in D12. Yeah. Okay.
If you guys are curious, I got an 85.
So okay. Good catch. Yeah. 85.
Yeah, I was at 5.
Yeah, I didn't think about that. Yeah.
Thing and
Oh yes.
will take home be a separate grade or will you change what you're?
It will change these grades, right? So currently what is happening, okay, how does it work is that midterm 1 by default is weighted 20% of your total grade. Currently, your exam midterm 1 is weighted 20%. But the moment I introduce that, it will deflate it accordingly. So what I'll do is that I'll hide this or make this weightage 0 and the other one will be, the new one will become your full score. Yeah, so it will act like a normal midterm. So that. After I do it, it might be more obvious than me telling me how I. Any other questions? This is how it is going to be, like we'll have about two of them, like there will be midterm two. And there will be a final exam. Final exam is also very similar. It's just concentrating more on the whole of the semester. Yeah. More questions? Seems like you have one more.
We're trying to figure out what that sound was.
Not kidding.
We were trying to figure out what that noise was.
Oh, that might be liquid helium, right? You got working on liquid helium, is it? Could be, huh?
You.
Who works in Igor's lab? This is Igor's lab, right next to it?
it's Igor's lab. I didn't know we had a student.
Abhiyan works with him and. I think they're. At this point, maybe because of, there's. But I usually see liquid helium moving around from here to there, so I think. It's pretty active here. Okay, so. Still go? Yeah. So. Midterm two, that's quite far. We'll have it exactly like midterm, one. 4 6. I haven't posted this yet, I'm still. Working on it, like, how exactly to. Changing, few things. And, it will be on quantum mechanics, so. Probably you've seen it here and there, so it might be easier. In that, sense. Final exam for this course has been. Announced. So it's December 12th, Friday. 8 to 10. AM. And there's also an unrelated. Information. This week's physics speaker. So. Is going to be a YouTuber. Look up. And how many of you have attended the physics seminar? Yeah, so it's expected that every grad student is supposed to be there, so we don't take attendance, but the expectation is that. That it is, everyone should be attending regularly. So, try to make it a habit. And this should be interesting, this is about. Places, he runs he was an undergraduate student here, so that's interesting. At least he was in my class, 10 years back, that's a nice thing. And he's around from Illinois. And he'll be there for discussion, so feel free to, we should be there around in students' lounge most of the day. Yeah, that's all. Anything else you want to bring up? Okay. Here I want to say a few things about quantum mechanics, the mathematics that we use for quantum mechanics. That's what I want to bring up today, and only for 2 lectures, which is mostly there in every quantum mechanical course, but put them all in some simple structured form. One is, of course, the matrix mechanics part of that, and the other I want to insist is derivative part, how you define derivative in quantum mechanics. So that's something we can talk about. So what's the difference between quantum mechanics and, let's say, Newtonian mechanics? Yes, that's it.
Use operators instead of variables, and like, I can't measure one thing and then always measure the other thing if they don't compute.
Yeah, so. That's a correct statement. It seems like the way we understand quantum mechanics is that normal numbers doesn't seem to satisfy. Uh, uh, satisfy the properties of the system. For example, let's go back to Newtonian physics, right? So this is classical physics, what we say classical, but let me say Newtonian physics. If you go back and ask if you have to teach Newtonian physics to some eighth grader, or let's say someone who knows calculus, right? That is the best. The first thing you would say is that physical quantities are represented by functions, like because we want to use the idea of derivatives. So idea is first you say that there exists time, right? So you don't define time, so there is time. And then we say that there is position, which is a function of time. Then say x as a function of time. Notice both these are not defined, but we are saying there is an idea of a function. And the moment I have an idea of a function, so this is function. This is Newtonian physics, but it could be anything else. Imagine that you're doing financial mathematics, and you could be studying the stock value of a value of some stock, and then again you would say this is a variable, and the value, the price of a commodity changes with time. Again, a function is defined. Once you have a function defined, then you have a derivative, right? You immediately say derivative, so velocity. So this becomes a physical quantity. So the physical quantity as velocity as a function of time is equal to limit L to t tends to 0 of change. And let me say, just to make it more general, let me say this is function, just so that we don't get distracted with the idea of x being position. So that's delta f over L to t. This is what we say df by dt, right? So this is a very concrete, well-established concept we have in calculus. These two are, say there are variables, there is one variable that depends on the other, that's a function. From that point on, we know how to proceed. Then we do acceleration, and we can bring in models which describe the motion. Now, what happens? Why do we need quantum mechanics to begin with? Let's say this is quantum mechanics. Can we use the same idea in quantum mechanics? And not necessarily. If you were to think of quantities, like one of the quantities that strikingly comes up is spin. So let's say spin. And what do we understand by spin of a particle? Spin of an elementary particle? Or spin of an elementary particle? What is a spin of an elementary particle? Anyone?
It's an intrinsic angular momentum that doesn't have a classical analog.
And what do we mean by intrinsic? Yeah, correct statement.
And believe the material,
Tell it again.
like it's
I don't know.
why,
It's self-contained within the particle, it's independent of its environment.
So maybe it does not depend on time.
It doesn't depend on time or
Right.
position or anything.
When you say mass of an object, it doesn't depend on time, right? It doesn't depend on position, like the mass of our planet does not depend on time or position where you are. So these variables are out of picture. Which also means that we don't know how to write it as a function. In fact, if you were to write so S will be for let's say for an electron, this comes out to be h bar over 2. That's it, it's a number. Let's say h bar is a universal constant. And what is h bar? Value?
Small.
Small. Yeah. Small is always with respect
the minus something.
Good, yeah, 10 raised to minus 34. Okay, 1.1 into 10 raised to minus 4. What are the units of h bar?
The joule seconds.
Joule seconds, that's very good. That will be the angular momentum. So whatever is the angular momentum, that will be the units of spin. What about z component? This is the z component of spin. S is a vector, and more generally, it's a spinner. But for our purposes, it is like an angular momentum. We will say it's a vector. So let's talk about one of its components. That's a z component. Right? A vector has 3 components. Let's say in the vertical direction, and it turns out we represent it by a matrix, by a 2x2 matrix. A very simple 2x2 matrix. That's what is the is a spin of an electron. Like we say mass of an electron, this is the spin of an electron. This is a component in the z direction. If you ask how does this change with time, like you're usually interested in spin is like a top electron keeps moving around, and you would like to do a time evolution of that concept, right? How does the spin evolve in time? That's something that's dynamics of an electron. But it has no time dependence. Right? There is no time dependence. How do you do differentiation? Like if I know function as a function of time, I can do differentiation, but there is no time here. So what do you mean by dynamics to begin with? If there is no meaning for dynamics, if there is no time in them. Talk about dynamics. Is a restriction. So let's say, let me do this here. So analogy, maybe this is. So whatever is a variable. That's not equals ladder. Yeah. Okay. So I said time just as a possibility. It doesn't have to be time alone. It could be position, it could be rotation. It could be rotation, and it could be translation. So there are many other parameters you can talk about. It doesn't have to be just time. In general, is it possible? Can we keep proceeding? And so what? Okay. Is it this room? Maybe we can ask them to see.
It sounds like it's through that wall.
I have a valve here, yeah. Can I ask?
Come to that.
How is really maybe they stop this one. Okay. So the time here represents lambda just because it doesn't have to be time. It could have been an angle, it could be rotation, that could be other dependencies. F of lambda, which is if it was time, it would have been f of t. Here, what we want to talk about, it is no more time, but there is going to be a generator. This is G. Instead of time, we will talk about generator of lambda. The time evolution or rotation will be done using a generator. And here, this will be the physical quantity itself. Let's say this is X. It could be F itself, doesn't matter, but I'll upgrade it to X. That's the idea of an operator. So all this will become operator.
once you have these, once you have a function in classical mechanics or Newtonian mechanics, you would define derivative as df by d lambda is equal to the limit lambda tends to 0. Right, that's the standard mechanics. And now our question is, what is dx by d lambda? We are interested in time evolution, but time evolution or how dynamics happens. And this is what quantum mechanics tells us. This is the mathematics of quantum mechanics. If you want, once you know the derivative, then you can do a lot of stuff with that derivative. Same thing here. Once you have defined derivative, once Newton told us how to take derivative, then we could build the whole mechanics out of it. Here, it is given in terms of commutation relation. This is x, comma. That's the basic governing mathematical prescription for quantum mechanics. And here we will do examples of how this really gives us equations of motion and so on. Since these are commutation relations, it usually, so maybe I should mention, usually x and g are matrices or operator or anything that allows you to take the commutation something non-commuting to the existing. Even in Newtonian physics, you have constructions like Poisson bracket, which allows you to do that. So it is not that it's only in quantum mechanics you see that. But of course, the time dependence when it's not there, quantum mechanics is the best place where it comes in. So all this involves operators, and matrices are good examples of that. Matrices are something that does not commute. So, and 2 by 2 matrices are the simplest matrices. So we come back and do some things of some physics that can be analyzed using 2 by 2 matrices. And spin happens to be the easiest for that. So let's do the mechanics of spin, and even better, even the simplest of them, they will just measure one quantity, so the z component of the spin, rotate the system and measure it again. And that's what I think Jackson was pointing out earlier, that if you make a measurement in quantum mechanics and then you change the system, then if you make the measurement again, it doesn't seem to stay in the same place. So the statement is that measurement disturbs the system. So let's analyze that. So a simple, quantum measurement maybe, or quantum analysis. I don't want to say measurement. Measurement has more, has a bigger meaning in quantum. What we typically do is that usually there is an operator A or physical quantity, like a quantity A. Let's say A, right? This is A, and that's the mathematical letter A. And if it is an operator, then you find its possible eigenstates, and usually that is described by O1 is equal to, this is A1, 1 plus A2, and so on. What do I mean by this? Remember, we were, so recall even in your exam, you had this, that in 2-dimensional space, we had 2 unit vectors, I hat I hat plus j hat. J hat, right? So we wrote a dyadic construction out of this. This was two unit vectors constructed together as a outer product. This is the same idea here. This is a unit vector if you want. Together, they form a complete set. So this is a statement of completeness. If I operate this on a vector, it gives me a component. And similarly, if I operate this on a vector in quantum mechanical space, which is usually called the Hilbert space, then it will give me the projection of that vector or of a state in on the eigenstate. So we first usually, the moment you decide that I'm going to measure A, what you have to ask is what are the possible eigenstates? So AI here are the possible eigenstates of A. You're measuring A, what are the possible results you can get? It will be A1, A2, A3, and so on. If it is a 2 by 2 matrix, there are only two possibilities. Right? So there will be simplicity, so it will be only two, and that's what we will deal with. Similarly, if there is another quantity, B, will have another set of eigenvalues. So this is P1, P1, and so on. Exactly like it could be polar coordinates. You have another set of bases which can explain or which can describe the same system. What does quantum mechanics do? You first measure A. So this is the measure A. And then you also select. It's not necessarily be selecting it. The act of measurement involves a selection of one of these states. So out of all these 1, 2, 3, I select one of them. So the moment you measure some quantity, like typically how do you do physics? You will say, oh, what is the initial velocity? You measure that. And then you wait for a while, and then you measure the final velocity and then compare the two. That's a simple physical process. Here you're measuring A, and the moment you measure A, intrinsically you don't have a choice. You have to select one of them, or the system will select one of them. It is not
For the comparison or what?
not for comparison, but that's what measurement means. If you don't select anything, that's an independent system altogether. So, or it's a different act altogether. Does that make sense? Like, for example, I'm saying you have a spin and you have a magnetic field. The only thing you can ask is the spin in the direction of the magnetic field or is it in the opposite direction? By that, we mean that the component of the spin in the z direction is the only thing that is well defined in this case. The x and y component, we cannot say much about. You cannot simultaneously measure it. That's another way of saying it. Does that make sense?
Measure, then the state will be again changed.
It will change, yes. So in a definite way, you can only measure this. If you measure the rest, you can still measure it, but then it will disturb the other system. But any quantity, if you measure, it gives you, these are the results it will give you. Maybe that's the way to look at it. Does that help? Clarification? Ask me more. That's a relevant question.
I feel like when we measure the system, then definitely that affect the whole system.
Correct.
Yeah, then we can take anyway the original system, or we have to
We
go with
cannot. We cannot.
we have to go with the new system again.
Not only new system, you disturb the system.
Then our system is unstable if we go for the measurement anyway.
Correct. But you can be clever and make sure to measure certain quantities that does not disturb the system. For example, like the spin again, So if you have a spin S, let's say this could be a vector S, right? That is the magnitude of the vector. Then there is S of X, then there is S of Y, there's S of Z. These are three components of the vector. This is the magnitude of the vector. If you measure the magnitude, you're allowed to measure that, it will disturb the system, yes. But after that, if you measure SC, you do not disturb the measurement of the magnitude. Okay. But now, after you measure the Z component, if you come back and measure the Y component, you have disturbed Z.
Sorry, I didn't get you.
So if it's write it, if SC is measured after measuring after S, it does not disturb measurement of S. Does that make sense?
Oh, yeah.
But on the other hand, so I'll give you a counter example too. If Sx is measured after measuring Sc, then it will disturb Sc. Is that clear? If I measure these two quantities, they disturb each other. If I measure these two, Sc and S, it does not disturb each other. So in a system, there are always quantities which does not disturb each other, and there are quantities that disturb each other. So in quantum mechanics, you're restricted to work in a confined region. You don't have the choice to measure everything, like position and momentum. You cannot measure them together. You have the choice to measure position, all three components, fine. But the moment you measure momentum, you're disturbed the position. What mathematical principle decides which one can be measured and which one cannot be measured?
Definitely, that's SFX.
Yeah, in this case, yes, but in general, if we are doing some new physics, then what tells you what will you look for when you want to explore? Oh, I want to measure this. Commutation relation. So if they commute, that means they can be measured simultaneously. That means one after the other, it doesn't disturb the system. So in general, if A comma B is equal to 0, then A does not disturb B. By this, I mean the measurement of A does not disturb the measurement of B. So there is more detail in that. If this is not equal to 0, then A disturbs B. So that's why commutation relations become a central piece in it. And again, it is clear here also, right? Notice commutation relation. If this is not 0, that means this changes. Like derivative changes, right? With respect to something, it changes. Like the idea is, what is the generator? What does it commute with? So what is the quantity that it is changing? That might be harder to discover, but whatever it is, if there are two operators, we can analyze whether it's disturb it or not. And because we have this restriction, we always work with a smaller subset where things don't change. That's the clever part of it. We still are able to do a lot of stuff. Just we make sure that we will never measure things that disturbs the system. I got in that sense, this that's. So in that context, I mean, so measure A, and that involves selecting an eigenvector. So that's what the mathematics that I want to do is the idea of finding what these eigenvectors are. So which is diagonalizing matrices, which probably some of us already know. First measure, and then the system evolves, and then again do measure B. And then select. And by I mean I'm selecting one of them, right? 1, 2, 3. I select one of them. That's my initial. And the final one, it could be B. And let me call that. But this is a two-step process. This measure A, and then it selects one of them. And by selecting, I can select two states if I want to. I don't have to be always selecting only one state. I can choose to select 2 states out of 5. I can select 3 states out of 5. I can even decide not to select anything. Right? I do not select any one of the eigenstate. That's also an option. So those will be the discussions one can have. We won't have so much time to just explore all those possibilities, but I'll give the basic idea because we'll be spending 1 week on. Once you have done this, so physics in quantum mechanics involves measuring 2 quantities or observing 2 quantities, and then we decide we have to make some conclusion, and that's decided by what is called probability. But probability of what? So probability of finding a system in BF if we have already found the system in AF. Like after I have selected this, what is the probability that the system will be found in BF? So probability of finding BF if we selected a initial. And this probability will be given by, let's project it. So you start with AI. So usually this, so maybe I'll write it in this form. So this is AI. Right, and then project this onto the state. And that's not a number. Notice this is, if you think of it as a dyadic, this is a dyadic, that's a dyadic. I construct a dyadic out of this. That's not really a number. So I have to take a trace. But the trace is cyclic. And remember, A, B, C, trace of A, B, C, D is the same as trace of B, C, D, A. It is cyclic. So I can use that cyclic case and make this project onto BF. And I learned that this is AI, BF times BF is AI. And using the idea of a scalar product, this is a complex conjugate of each other. So that's I have magnitude of so that will be our prescription. So that is a very simplistic summary of a very simple quantum mechanical system. Measure A, measure B, and find the probability, right? And here I want to do this for 2x2 matrices, which is pretty much done for spin. Whenever you're measuring the spin, that's exactly what we do. We find eigenvalues, eigenvectors, and we will be able to get these probabilities. So let's talk about the quantity A, which in our case will be a matrix. So let A be equal to a matrix, let's say. Yeah, let's do the simplest one, so it's 1, 0, 0, -1. And if that's a matrix, what are its eigenvalues? What are the eigenvalues of A?
1, 0.
1 and -1, correct, very good, so eigenvalues is 1 and -1. What about eigenvectors?
0, 0, 1.
And what are eigenvectors, by the way? Define eigenvector.
It's if I subtract like the eigenvalue times the identity from that matrix, I should get the zero matrix that maps to the null space.
Or you can say that A applying on an eigenvector, so let's say A acting, or let's say, let me write this as. I would like to have some vectors, 0, -1, acting on some quantity, it doesn't have to be real, so I'm writing this as complex, so Z1 and Z2. We have to find a vector on which it acts, then it should give either 1 or -1. So this should give me a 1 plus 1 times Z1, Z2. So what is such a vector that will give me a +1? So this will be called E1, let's say. It's plus and minus, let's say E1. And similarly, I would like to know 0, -1 acting on another, so Z1 prime, let's say. It will be E2. It should give me -1. Okay. And how would you do that? So that's an equation, right? We can solve for this. This is an equation. So I should be able to solve for that. So let's solve for Z1 and Z2. That's equal to Z1 is equal to, right? Z1 plus 0 is equal to Z1. Our second equation is minus Z2 is equal to Z2. So what's the solution for that?
Z1 equals 1, Z2 equals 0. Or Z1 is anything, but you want to normalize it.
Yeah, so this is saying, yeah, how do you solve this?
There's only one solution to minus Z2 equals Z2, that's 0. So we at least know that the bottom component is 0.
Bottom is 0, so x is equal to Z2 is equal to minus Z2. Yeah, so that is only 0, right? So this is equal to Z2 is equal to 0. And Z1, there are many solutions possible. So you leave that alone and you say, if I know one solution, there are many solutions. So Z1, sorry, many solutions possible. So what are the solutions for E1? There's 1, 0, 0, -1 times Z1 times 0. And let's check whether this really gives the answer or not. So it is 1, so this just gives you Z1, and this is of course giving you 0. So this is +1. So it is indeed correct. So this is an eigen vector. You can remove the Z1 part, so make it normalize it. So you say that I want this to have a unit vector. So let Z1 be equal to 1. And that is the idea that if you have a vector space, if any quantity that is in the direction of the eigenvector is also an eigenvector in general. is a directional quantity, it only gives the direction. So if I choose this, so then E1 is equal to 1. And similarly, the E2 you can, so similarly, quiz, right? Quiz. Find that E2 is equal to
0, 1.
0, 1. So it will give you the. So you decide that, okay, I'm going to select, I'm going to measure A. And there is one of them, you can always probably have the choice that you can select it to be in the first eigenstate, and then now you have to measure something else, and preferably we want to do a measurement which really disturbs the system so that we can talk more. Probably, if you keep measuring A, it'll give you back the same thing again and again. So let's do another quantity. So let's have B. So let B be equal to, or maybe before that I should say. So 1 now is equal to E1 plus E2 where E1 is equal to 1, 0 and E2 is equal to 0, 1. And the eigenvalues associated with the 1 and plus 1 and minus 1, that's also important. Okay, so let's do B now. Introduce B. Well, let B equal to 0, 1, 1. That's a 2x2 matrices. And these matrices have some importance. They are relevant for spin. They are called polymatrices. I'll introduce that in the next lecture in more formal way. But now these at this point we have a matrix, and in this case it was easy to find the eigenvalues and eigenvectors. So now how do we find the eigenvalues of this quantity? So is there a formal way of doing this? So the formal way is the following. So notice what was the language here. I have a matrix. Multiplying this should give me its eigenvalues. So I have 0, 1, 1, 0. Acting on a vector Z1, Z2. I'm now interested in it should give me an so this is an eigenvalue for Z1, Z2. So this is eigenvalue. And that's eigenvector. Put it on the other side, you can always say that this is the same as lambda 0, 0, lambda times Z1, Z2. Put it on the other hand, and you learn that this is the same as minus lambda 1, 1 minus lambda times Z1, Z2 is equal to 0. That's a linear set of equations you can solve for. And seems like there are more unknowns that are solved for Z1, Z2 and lambdas. But since the right hand side is 0, the only non-trivial solution you can get is when the determinant of this is 0. Otherwise, it is not meaningful to explore that at all. So this implies that you want a non-trivial solution, determinant of minus lambda 1. That tells you. So that tells you that lambda square minus 1 is equal to 0, and you have lambda is equal to plus minus 1. It just turns out it is just a coincidence that these 2x2 matrices also have the same eigenvalues, but that doesn't have to be the case all the time. If you are having two different 2x2 matrices, it might have two different eigenvalues. In this case, both have plus and minus 1. The moment you have the eigenvalues, you look for eigenvectors. So this time we have to look for +1. So what we do is go back and substitute it back in this equation so that we can solve for z1 and z2. So let's look for the eigenvector corresponding to +1. And you get +1. Here will be -1, 1, 1, that's 1, and z1, z2. So first we solve for the eigenvalues, put the particular eigenvalue back, and you're looking for the particular eigenvector. And here now you get an equation. So this is a linear set of equations. Usually the two equations that you get are not independent. So you only one information. This is z1 minus z1 is equal to z2. The second one is also z1 is equal to z2. So what the best we can learn is that z1 is equal to z2. Remember, in the earlier case, the best we could learn is that z2 is equal to 0. There's only one condition. So it is z1 is equal to z2, and anything that satisfies that is sufficient. But you can, or let's just, so z1 is equal to z2, so then you immediately say choice could be, so this is a choice, so this is 1 over root 2, right? So this is a choice. Like I just need one eigenvector, I make that choice, and then that is 1 over. I can also make it normalized and get this in a more formal way, but that is only making it seem like that is a choice, but you really don't have. This is really, we are making a choice in this thing. So our eigenvector would be u1 would be equal to 1 over root 2 times 1. Do the same if lambda is equal to -1. This is minus, so this time this becomes 1, 1 and +1. And this time z1 is equal to minus z2. That can be 1 over root 2 again, and e2 then, and maybe I should write this way. That's your 2. Oh, I should not write e1 because I used e1 for this purposes, right? Can I again go back? Sorry, I think since these are eigen vectors of A, it is good to write this as A1 and A2, right? Instead of writing E1, that might be a better notation. So this is A1, A1, A2, A2, so this is A1, and here it is B1 and B2. And we again have 1 is equal to, this is 1 plus. I say it as if it is a requirement or as if I'm imposing it. It always comes out like that. If you find 2 eigenvectors of a matrix, it will always satisfy this condition. Right? It is complete. So eigenvectors by construction are complete. So it will always satisfy that. If we have this, let's do a simple system. So now we go back to our system. We measure A, measure B, and talk about probabilities, right? So can we do this? For example, so measure A and then select A1. So select A1. By that I mean this is 1, 0. That's a choice I made. And how do I do this? usually this is done using a magnet. When I'm selecting, what I'm basically doing is that aligning the magnet in a particular direction. So that's what I'm doing, that selection. How do you say this? Let's say, like this could be a magnet. And there is a beam with electrons coming with magnetic movement in all directions. So this is a measurement now. And I have the choice that the system could go to the left or to the right. So this is if I close this and if I select this. So this is the selection. So this is a measurement. And this is selection. If you have heard of double slit experiment, like whether you close one of them or the second one, that's the idea here. So you have to do something to the system to be able to allow it to proceed in the forward direction. If you do not do any selection, that's also a choice you make. Like that's also a possibility, and that will involve a measurement without any selection. And that's also a valid description. So if we select this and then you keep going, and then so that's your measurement A. So this is A. So that's your A. And then you say this is B. You again come back to this, and now you would select that this is B file. So again, you say that this is measure B. And select let's say B1 to be equal to 1 over root 2 and 1. You could have selected either one. B2 is also a possibility. Is that clear what we're talking about? And the probability of finding a selection of B1 after you have selected A1 is the following. So you just say so B probability of 1 to 2 now, or 1 to 1. You select, how is it? Yeah. So yeah, usually I say this. So this is the language I use. So this is A1. You select A1 and then you go ahead and select B1. This is equal to A1 B1 square. We know what that is equal to A1 is 1 0, but this is in the conjugated form, so that's 1 0. And B1 is 1 over root 2, so that's 1 1. Then you have 1 over root 2 and square. And that's equal to 1 and 1. So that's 1 by 2, I suppose. So that's the probability. And you can do this for any system you want. Later on, we will have in general quantum mechanics, you have not just two states, there are multiple states, but this is the basic construct. And this process, when you're going from here to there, that is to be precisely talked about, is that here you're evolving the system. Often B is related to A, and that's where the commutation relations come. You would like to write B in terms of A. It is an evolution of a physical quantity. We will connect that with any questions on that. Your homework will be built based on this. Yes, you're asking something?
I think I have a little bit more question. That's why I keep it at for the last.
No, ask. Yeah.
Okay, if that one is 1 by 2, will be our
To A1, B2 square. That's equal. So this is again 1 0. But this time this is 1 minus 1, I suppose. This 1 over root 2. Something went wrong.
that's okay.
It ended it at 40 minutes because
We did log in, so it didn't record then.
it recorded the first part because I claimed host for it,
Oh, so you did, okay, yeah.
But I just logged back in, claimed host again. Okay, cool.
And that's 1/2. Notice, first you start from something, you have to begin somewhere. So if I select A1, what are the choices I have? I can select B1 or B2. There are only two possibilities, so they have to add up to 1. If there are 3 of them, all 3 of them have to add up to 1. That's the total probability. After you have selected. Now you can easily compound this. I can do A, B, and then C. That is where all the nice features come in of quantum mechanics, is that do this in 3 states, and there are interesting things like interference and constructive and destructive things that happen. All that is nice, but the basic idea I'm making is this, that you project one. So notice you start one and you're basically doing projecting, right? This is all that you're doing. You have a vector and you have another vector, you're projecting on each other. So that's the basic idea of counting. It has vector, the idea of a vector inbuilt in it, that you're projecting one on the other. So that's what I'm trying to highlight. And there are a lot of details, of course. You have to evolve and other things. I'm taking a very simple part of that. Yeah. Any other questions? I'll stop here for a change of. We will make this more concrete on Friday, and the homework will be due Monday.